In this video, we're going to look at slender columns. Our previous discussion on columns, we were looking at the behavior of a column with respect to its cross-section. So in this section, we're going to look at what happens when we consider the full length of the column. When we get longer columns, sometimes we can get a column that can't achieve the cross-sectional strength that we found of just our short section. So we'll see how to account for that in this section. By the end of this section, I want you to be able to differentiate between short and slender column behavior, determine whether slenderness needs to be considered in a column, calculate an EI effective for a given column using both the simplified and detailed ACI 318 expressions, calculate the effective length, or KL, for a column with a given end condition, relating our simply supported end conditions to other end conditions that we might have. Identify two ways that slenderness can be accounted for in columns. Create a moment-axial load interaction diagram with slenderness effects considered. And finally, use the moment magnifier procedure to calculate the magnified ultimate moment. If we want favorable column behavior, we need to make sure that our longitudinal steel doesn't buckle. So we looked at this in one of our previous sections, in our short compression member section 6. We need to also make sure that we don't have overall buckling of the column, which will be what we focus on this section. So buckling of our longitudinal steel would be a localized buckling within our column, and the overall buckling of the column would look at the entire column length and end conditions. In later sections, we'll also look at how we can control and ensure we don't have shear degradation, and we'll look at also the effects of reverse cyclic loads, but this will be in a later section. We can remember from before that to prevent the buckling of our longitudinal steel, we need to use close tie spacing, and we need to ensure that our ties are properly sized. So we started from our buckling stress expression, solving for a spacing over bar diameter. And then we saw that having a spacing over bar diameter of about 16 would ensure that we prevent the buckling of our longitudinal steel, or we ensure the proper mode of buckling happens. So having the right spacing of our ties will ensure that we don't have a localized buckling failure within our column. In this section, in this presentation, we're going to focus on the overall buckling of the column. So in flexure, we focused on and we found a certain flexural strength of our section based on its cross-sectional properties. So in our overall column, with a certain reinforcement, we looked at just the cross-section at one section along the length of that column. We use this cross-section in our rectangular stress block approximation to find our MN and PN for this specific section. So in short columns, we assume that this column strength found in the cross-section can be achieved in the actual column, but this isn't always going to be the case. As a column buckles, there's going to be some kind of out-of-plane deflection, or a delta shown here. This delta is going to cause second-order moments, or moments caused by deflection. So the axial load times this deflection will give us our second-order moment, or P delta. So this is sometimes called a P delta effect. So this second-order moment is going to be in addition to any other moments that are applied to the column, and thus is going to decrease the strength of the overall column. We consider a column to be slender when the second order moment decreases the capacity by more than 5%. So if our MN of the slender column is less than 95% of the MN of our short column, then this is considered a slender column. On the next couple slides, we're going to go through some derivations of different buckling expressions with different boundary conditions and loads. Some of these equations are actually found in the code, so you don't necessarily need to know the derivation, but you can see where some of these equations come from. And a lot of these things are taken from different stability courses. So just remember that the difference between statics and stability analysis is for our stability analysis, we're going to look at the deflected shape, where in statics we looked at the undeflected shape. So we're going to start our derivation first looking at no lateral loads and pinned connections. We'll assume that our column has a stiffness EI and a length L. Our distance along the length is x, and our transverse deflection is y. And we have an axial load of p on this column. With this column, we can define our secondary moment as p times y. We know our y is going to change along the length, so our secondary moment's also going to change along the length. We can then find our moment equal to our moment is equal to py, which is equal to negative ei times d2y dx dx2, so the second derivative of our y, or our displacement. We can rearrange, and then we have this differential equation, and we can define lambda squared as pi, and we'll have this ordinary differential equation to work with. With our, so we have a second order ordinary differential equation shown here and equal to 0. So with this second order ODE, we have a homogeneous solution and a particular solution. For us, for this equation, our homogeneous solution is shown here. So y equals a sine lambda x plus b cosine lambda x. Our particular solution in this case, we don't have any because our second order ODE is equal to 0. So we can use this homogeneous solution and solve for some of our constants using our known boundary conditions, which we'll do on the next slide. We know that our deflection at the left end, or where x equals 0, is 0, and the deflection at our right end, where x equals L, is 0. So we can use these boundary conditions to solve for our different constants. The first one would give us that b cosine 0, or b times 1, or b, equals 0. And sine 0 is 0 here, so that takes out this term. So from the first boundary condition, we can see that our b is going to be equal to 0. From the second one, we can see that our y of L, or a sine lambda L, is going to be equal to 0. And so this means that either a equals 0, so our constant out front is equal to 0, or lambda L is equal to n times pi, where n is going to be equal to 0, 1, 2, 3, etc. So a not equal to 0 and n not equal to 0 would give us a non-trivial solution. So this is what we're going to use on the next slide. If we have a non-trivial solution where a is not equal to 0 and n is not equal to 0, then we know lambda L needs to equal n times pi. If we square both sides so that we can substitute in our known lambda squared expression, we'll come here. So we're lambda squared times L squared equals n squared times pi squared. We can substitute in for lambda squared and then solve for p. And we'll get an expression n squared times pi squared EI over L squared as our critical buckling load. The first mode, or n equals 1, the first buckling mode, will give us our lowest buckling load, or our most critical buckling load. So then we'll just have p squared times, or equals, pi squared times EI over L squared. And this is our Euler buckling load, which again we derived with a simply supported column with only axial loads and no transverse loads. We can next look at the case where we have a simply supported column with an axial load and a transverse load. So with this column, we'll have a deflection from our transverse load, our primary deflection of y0, and our magnified deflection of y0 plus y1. So I'm not going to go through the derivation here, but you could, again, start with equilibrium of your deflected shape, and we can solve for M max, so the maximum magnified moments, and we could also find the maximum magnified deflection. But so you can see here, our M max is equal to our MM. So this is the moments just from our transverse load times this additional factor. So if we define Cm equal to this term here, then we can see that our M max is just going to be equal to MM, so our moment from our transverse load, times Cm over 1 minus alpha. So, and alpha is the relationship between P and P critical. So this is kind of the moment magnifier concept, is that our second order deflection, or yeah, our second order deflections will magnify our moment. So mm times delta. And this Cm term, ACI will conservatively take as a 1.0 for braced frames in this case. We can also look at a simply supported case with different end moments. So with an end moment of M1 on the left and M2 on the right. Again, we can start from our equilibrium of our deflected shape with our moments, and not going through the derivation, but eventually solve for our M max. And in this case, we have a different Cm factor dependent on our end moments and the relationship of M1 to M2. So we'll see in ACI, when we have different end moments, we'll find our Cm with the relationship between our smaller and larger end moments, and whether we're in single or double curvature. So we'll have a little simpler expression, but this would be the exact Cm from this derivation. So on this slide, you can see the simplified Cm expression that's given in ACI. Here's the detailed Cm expression that we just derived on the previous slide, and here's the simplified expression. So Cm equals 0.6 minus 0.4 m1 over m2, where m1 over m2 is negative if the column has been in single curvature and positive if it's in double curvature, and m1 is the smaller of the two moments. You can see that it lines up pretty well with the theoretically accurate expression, and it's simpler to use, so this was the expression that's given in the code. Our CM is also going to change if we allow joint translation, which happens in sway frames versus brace frames. So if we allow joint translation, it's just like looking at half of our previous column. So half of our previous column here. We can use this as a starting point to derive a new CM, which we can simplify to this CM here. And ACI conservatively takes CM equal to 1.0 for our sway frames. So that'll simplify our calculations a bit. We can next look at a simplified derivation for a moment magnifier, deflection magnifier based on our second order effects. And for this, we're just going to look at a pin-pin column with a hinge in the middle and a spring with stiffness K, resisting the deflection of that hinge in the middle. We'll have kinematic a displacement of the structure, so it'll just be a straight line deflection. And we can see then that our axial load and axial load will resist each other, and we'll get a force resisting the translation of this middle hinge equal to k delta over 2. So we can sum our moments about the top and just have our p delta equals k delta times L over 2 to get our p critical equals KL over 2. If we add in here an initial deflection, delta naught, then we'll have a total deflection equals to delta naught plus delta. And again, from our moment expression, we can get down to our P delta total is going to be equal to P critical times delta total minus delta naught. And then we can relate our delta total to our delta naught by dividing by 1 minus P critical. And we can remember here that our P critical is equal to KL over 2. So this is similar to the form of our moment magnifier that's given in ACI, where we have our moment with slenderness considered equal to our moment without slenderness times some magnifier delta. And in this case, our delta is going to be equal to Cm, which takes into account our different end moments and our transverse loads, and whether we're sway or non-sway, divided by 1 minus Pu over 0.75 P critical. So where our P critical here is just pi squared EI over KL squared. So you can see that this magnifier component is similar to the magnifier that we saw on the last slide with the Cm factor that we found on our slides with different end conditions and transverse loads and sway frame. So now we're going to look at how to calculate all of these terms as we work through the rest of this section. So our EI effective, our K factor, and how to actually use it to find the magnified moment. We're first going to look at when do we consider a column to be slender. So we'll see how to use that KL over R term and how to use that to determine if our column's slender or not. Then we'll see how slenderness affects the strength of our column and how to account for the decreased strength that slenderness can cause. We'll see also how to determine EI. So EI, we need to make some assumptions and approximations for our reinforced concrete members. We'll see how creep and long-term loading is going to affect our behavior. And then finally, we'll look at how we can determine the effective length for our column based on different end conditions and using our alignment charts. We can remember that a column is considered to be slender if our capacity considering slenderness divided by our capacity just looking at the section is less than or equal to 95 or 0.95, 95%. So if our slenderness causes greater than a 5% decrease in strength compared to our sectional analysis, then we need to consider slenderness. So ACI or researchers have gone and looked at this relationship and determined what KL over R values will be our criteria to see when we need to consider slenderness. So for ACI, we can neglect slenderness when in a sway frame when our KL over R is less than or equal to 22, or in a non-sway or braced frame, we can see when our KL over R is less than or equal to 34 plus 12 times M1 over M2, where M1 over M2 is negative if the column is bent in single curvature, and M1 is the lesser of the factored end moments, and where KL over R is less than or equal to 40. So our R here is equal to our square root of I over A, and our K is our effective length factor. ACI offers both a simplified and detailed procedure or equation for finding our EI. Our simplified expression just considers the stiffness provided from our concrete. So you can see that our simplified is just 0.4 times EC times I gross divided by 1 plus beta DNS. So we'll talk about beta DNS in a second. Our detailed expression considers also the stiffness provided by our steel. So it includes this ES plus ISE term. You can see that our simplified expression will do a better job for low or columns with small reinforcement ratios because it doesn't consider the steel, but it'll be conservative with really large amounts of reinforcement, so high reinforcement ratios. And our detailed expression will do a better job with larger reinforcement ratios. So here where our rho equals 0.8, we're going to be closer to 1.0. So actual stiffness is right around where our estimated stiffness is compared to here where we're overestimating or underestimating our stiffness quite a bit. So the detailed expression does better with large amounts of reinforcement. We account for creep in our column with this beta DNS term. So this beta DNS term is just the ratio of our P sub U sustained divided by our total P sub U. So the larger amount of load that's sustained, the smaller our stiffness is going to be. And that's going to be because our creep effects are going to kind of soften our section. So this beta DNS term accounts for that. You can notice that one of the shortcomings of the expression is this beta DNS in the detailed expression modifies both the concrete and steel components of the stiffness, when in actuality creep will only affect the concrete component. There have been researchers that have proposed alternate equations, but none of these have been adopted. So right now, this is how the creep is accounted for in the overall stiffness of our column. The effective length factor, K, allows us to determine an effective length, which allows us to use the simple critical buckling load expression for any end conditions. Our K we can find using our alignment charts. So we have a different alignment chart for non-sway and sway frames. To use these alignment charts, we must find the psi factor for each of our end conditions, for the end condition A and for the end condition B. The psi factor is the summation of the column EI over L values divided by the summation of the beam EI over L values. The beams provide stiffness to the columns to restrain the columns from buckling. The psi factor varies between 0 for a fixed case and infinity for a pinned case. So if we have a fixed column, we'll use a straight line between our fixed end conditions, and we'll see a K factor of 0.5. If we have a pinned column, we'll get a K of 1. And another common example is if we have a pinned fixed column, we'll use a straight line between the two, and we'll get a K factor here of 0.7. So other end conditions can be found using the psi equation that we talked about and using the alignment chart with a straight line between the two end conditions to find our K. There are a number of assumptions that go into this, this equation. Since this isn't a stability class, we're going to need to make several assumptions. The first is that our column and beam stiffness is the same. Second, our beam stiffness is 6EI over L. Third, we have no axial load in our restraining members. So we'll assume that our beams are restraining members and our columns are the members being restrained, when actually you can have columns that are acting as restraining members, or you can have beams with axial load in them, which would decrease their effectiveness to restrain the columns. We can also assume that all of our columns in the story buckle simultaneously. So we'll evenly distribute the stiffness provided from the beams. And we can also assume that our total joint restraint goes equally to the columns above and below. If this were a stability class, we could make a number of different modifications to this expression. So one modification that I'll touch on is if we have different beam stiffnesses depending on different end conditions. So this is the typical assumed case, is just a sway portal frame, where we have a stiffness of our beams and our columns equal to 6EI over L. So we can modify this stiffness if we have different conditions for the end of the beam. So over here, the far end, considering the restraint provided by this beam on the left column. So if we have the far end of our restraining member as pinned, for sway and non-sway, our stiffness would change to a 3EI over L. So this would mean that our M factor would be our stiffness, our actual stiffness 3EI over L, divided by our assumed stiffness, in this expression 6EI over L, so 3 divided by 6. And for our no sway, we would divide our 3EI over L divided by 2 here, so 3/2 for our M factor. If we have a far end of our restraining member as fixed, it would change our stiffness to 4EI over L. So in this case, our M factor would be 4 divided by 6, our assumed case. And in our no sway, 4 divided by 2, which is our assumed case for no sway. So we could use these M factors depending on the different end conditions of our restraining member to modify this M times EI over L for the beam on the bottom here. So there are other modifications that we can make to our equation here, both on the bottom and the top. So you can take a stability class or look at some online searches for stability to see some of the other modifications that can be made. For reinforced concrete members, we also need to approximate the stiffness of the restraining members. So we need to approximate the I to use in our psi equations. So ACI provides equations to use in the table shown on this slide to approximate the stiffness of the members. If we have a beam, we can assume that our moment of inertia is just 0.35 times the gross moment of inertia for the beam. For columns, we can see that the assumed approximate moment of inertia is 0.7 times I gross here for the columns. So we can use these values here to approximate the moment of inertia I for our members. Likewise, we can use our modulus of elasticity for our concrete to approximate the modulus for our columns. So we'll just use the ACI equation for EC in our psi equation. So using these approximations, we can calculate our psi factor here at both the top and bottom joints. Next, we're going to look at how we can actually account for slenderness and look at how our slenderness will actually affect our strength. There are two different options for considering slenderness effects. The first is we can apply our slenderness effects to our MN interaction diagram, our moment-axial load interaction diagram. So here we have our factored moment-axial load interaction diagram, And here we have our factored moment-axial load interaction diagram accounting for our slenderness effects. So you can see then, you can consider your moment and axial load combinations. So your different load combinations that are factored, but not considering slenderness. And you need to make sure that these points fall within our MN diagram considering slenderness. So this is one option for taking into account our slenderness effects. The other option is to magnify each of your applied moments. So for each of these MP points, so each load combination, moment and axial load, we need to magnify our moments and make sure that these magnified moments fall within our factored short column moment axial load interaction diagram. So you can see here on the left, we're looking at our factored points, our factored MP points without slenderness, and we need to make sure that they fall inside our moment axial load curves with slenderness. And on the right, the other option is to look at our factored points with slenderness and make sure that they fall inside our moment axial curve without slenderness. So we're either applying our magnifier to our demand or to our capacity, but just make sure that you're doing one or the other and not doing both. We're going to start by looking at how slenderness is going to affect the strength of our moment axial load interaction diagram. So we can remember with our moment axial load interaction diagram, when we apply a load at an eccentricity without slenderness effects, we're going to have a linear relationship. So if we apply a load at an eccentricity E, we're going to come out with a linear relationship until we reach the point on our curve that would cause failure. And we know that our moment is equal to our load times our eccentricity, or P times E. When we include slenderness effects, we're no longer going to have a linear relationship between P and M. So we're now going to have this magnifier delta. So our M max is then equal to P times E times delta, which is dependent on P. So we'll see that we no longer have a linear relationship. For our slender column, when we apply a load and eccentricity, we'll kind of start out linear, but then our second order moment effects are going to have a large impact on our applied moment. So it'll decrease the axial load required to cause the failure. Here you can consider, or you can compare the axial load required to fail the column at this eccentricity, just considering, or without considering slenderness, so just our short column, compared to our failure of our column with our slenderness effects. So B here. To construct a moment axial load diagram with slenderness effects, what we'll do is we'll find the axial load that'll cause failure with slenderness, and then we'll find the point or where this failure load would line up, not considering slenderness. So P fail, or the load required here at B, we'll slide over here to our axial load without slenderness. And then we'll repeat this for multiple points to get a new moment axial load interaction diagram here. So here we have a moment axial load interaction diagram without slenderness in black, and then in red with slenderness effects considered. We can then use this curve to determine if our slender column can hold different loads without failing. With this curve, we can see that this point here, MU1 and PU1, is okay for both slender and short column behavior. The second point here we can see would cause our slender column to fail, But if we provided bracing so that we had short column behavior, this point would be okay. And then the last point here, MU3 and PU3, would fail for both short and slender columns. So then our whole cross-section of our column would need to be modified. For this example, we're going to construct a moment-axial load interaction diagram with slenderness effects for the section shown below. We've been looking at this section in our short column section, so we already have the short column moment-axial load interaction diagram. So we'll see how to modify this to include slenderness effects. To find our slenderness effects, we need to know something about our column length and our end conditions. So we have a pin end conditions with different moments at the top and the bottom. And our overall column length is 20 feet. At this time, you can pause this presentation and go to the video for example problem 1. Next, we're going to look at the other way to account for slenderness in our columns. We're going to apply our slenderness to our demand points, mu, pu. So we'll magnify all of our different demand points here and make sure that they fall inside of our factored short column moment axial load interaction diagram. The first thing that we need to do is find the moment axial load interaction diagram for our section, so not including slenderness. And we'll do this using the procedure that we looked at in our previous module. We next need to determine if our column is actually slender. So ACI allows us to neglect slenderness when our KL over R is less than some constants, depending on whether we're sway or non-sway or braced column. So we remember our R factor is equal to square root of I over A. And remember that for these ACI expressions, our M1 over M2 is negative if our column is bent in single curvature, positive for double curvature, and our M1 is the lesser of our factored end moments. If our column is slender, then the next step is to determine our EI effective for the column. We can use the simplified or detailed procedure. We can use the simplified if we have a low reinforcement ratio. We'll use the detailed if we have a larger reinforcement ratio. And we'll note that these expressions do include our long-term effects. So the effective creep on our column is accounted for in this beta DNS factor. We'll next need to determine our effective length, or KL, using the alignment chart and our known end conditions. Remembering that infinity is for a pinned end condition and 0 is for a fixed end condition, and we're between 0 and infinity if we're restrained by beam members and we have something in between pinned and fixed. Then using our EI effective and our KL, we can calculate our critical buckling load, and we can also find our CM factor. So our critical buckling load we can find is just equal to pi squared EI over KL squared. So we can calculate that, and then also find our CM, which takes into account our different loading conditions. So here we have, if we have no transverse load, then we'll use this factor, and if we have a transverse load, then it's just equal to 1 for braced frames. And again, our M1 over M2 is negative if the column's bent in single curvature and positive for double curvature. Our next step is to choose an axial load, which will just be the P sub U for one of our demand points that we're looking at. And with this axial load, we'll compute our moment magnifier, or our delta. Note that there's a 0.75 stiffness reduction factor included, and this factor is based on the probability of understrength of a single isolated slender column. So if you're using ACI, include the 0.75. If you're not using ACI, then you can decide whether to include the understrength factor or not. just depending on your specific case. Next, we compute the maximum magnified moment. So our magnified moment is equal to our moment magnifier times our moment, or M2 or MU, sub u for the point. And then we need to compare this point that we just found, M sub c, comma P sub u, with our moment axial load interaction diagram for our short column. And we need to make sure that this point lies within our short column, our factored short column interaction diagram. And in this case, our design is okay because our point falls within our curve. Our next example is looking at the same column that we looked at in the first example, only we're going to apply our slenderness on our loads rather than our capacity. So at this point, you can pause the video again and go to our video for example problem 2. Shown here is a list of references for further study on slender columns.